Apologies, we were stuck in the traffic, so made it here. So thanks for your patience. So I just want to finish up what I started the last lecture. So we were talking about how to assess the solution quality, how to use it to sort of in sampling-based methods to stop the sampling or to believe we've got a good solution. But we've so far focused on the type of problems where we only have a deterministic set of constraints, right? Whereas a more general problem would have both, say, a stochastic objective function, which we write as expected value, but it can represent a lot of different things. Same here, right? We can have some deterministic constraints as well as stochastic constraints. And that's what we're going to focus on now. So let's say last time we focused on this. This time we're going to focus on problems like this, okay? Like a chance constraint. I'm actually going to talk about that. Equivalently, probabilistic constraints. All right. So in this one, in the other case, I told you, suppose this kappa is the set of, is representing the set of stochastic constraints. It was an empty set. Now I'm going to have some things in it. And let's see what's happening. Okay, so let's remind us the problem. Because we cannot solve this problem, right? The stochastic problem is very difficult, typically impossible. We cannot solve it. So we only have an approximate solution. What do we do in that case? How do we know it's a good solution? How do we know it's a bad solution? We also have a lot of sampling error if we use sampling to come up with that value, right? So how do we assess its quality? And if you recall from last lecture, we define it as the quality to be the optimality gap, right? So this is the objective function value minus the best we can do. And zero optimality gap, it's optimal solution. Otherwise, the higher the quality, the lower the optimality gap, obviously. And so just like before, we have the same problems. So again, as a reminder, we cannot evaluate this function. Even just one, sometimes this g can be very complicated, let alone taking its expectation for a fixed x. Of course, this is hopeless. We don't have the solution to the problem. But furthermore, when we have stochastic constraints, we don't know if the solution is feasible or not. Okay, I'm pretty sure Tito must have given this example to you when he talked about the stochastic constraints, right? If you have expected value less than or equal to 0, and if x is equal to 0, like it's on the boundary of that constraint, if c is normally distributed, no matter what sample size is, half of the time you're going to be saying infeasible, half of the time you're going to be saying feasible, right? It's actually a very hard, difficult detection problem. So we need to actually come up with ways to also statistically figure out if it's feasible or not, right? And some cases it's not that difficult. Some cases it can be a little bit more difficult. So we want to assess the feasibility. And on top of it, of course, just like before, so 3 parts. We had 2 parts before, now we have 3 parts. First, we want to assess the feasibility. Because if we don't know if the solution is feasible, why do we even care what quality it is, right? It's outside of our region. Once we figure out, or once we are reasonably confident that it's a feasible solution, then we can move on and estimate its objective function value. And that's, again, just like we did before, you can just take some sample size. I denoted here as NU, so you can actually separate the upper bound or this expected value estimation versus the lower bound estimation. So you take a sample size here, N sub U. Take your sample mean, use regular statistics, just like we did before. Okay, so I'm not going to talk about this that much. And a lower bound, this is not as easy as before. I mean, on the beforehand, what did we use to get a lower bound on this? We had a statistical lower bound, right? We solved the SAA problem, and its optimal value on average, there's an optimization bias. The bias gives us a lower bound. And so we can get some lower bound. This time, we don't have that because we have stochastic constraints, all right? Once we have stochastic constraints, that inequality does not necessarily hold, that easily, all right? So we need to do something more here. We need to pay more attention here. This is the same, and we need to pay more attention here. Okay? So in what follows, I'm going to talk about general expected value constraints, talk about some general methods to do them, and then some more specialized methods for probabilistic constraints. And I'm going to focus on the number 1 and number 3, and to kind of briefly mention how to use it along with the lower bound here. Okay? So the first one is going to be the problems with general expected value constraints. So, I mean, this general expected value constraints covers pretty much everything. You can, usually map it back to some expected value. Even the chance constraints, you can map it back. But of course, the type of function that you end up using is going to make it a very complicated problem, or non-complicated problem, or a simpler problem. So, just for simplicity, I'm going to take only one stochastic constraint, right? So we might have a whole bunch of them. Actually, in some cases, we might have uncountably many, infinitely many, like stochastic dominance constraints and stuff. But so just simply, first of all, let's assume finite, but then now let's assume only one, all right? Just one constraint. And generalizations are possible, at least in the finite case, right? So what do? The SAA, pretty much the same thing, right? Whenever we see an expectation, we take a bunch of samples, and then we replace it by the sample mean. We use the same samples. Now, this is our sample average approximation estimate, right, of the stochastic constraint. So, and then we optimize it. We still call it this new n value, optimal value of the SAA. Now, I want to do this. Give me a solution. It's feasible according to the deterministic set of constraints, right? So this is easier to determine. You might have to do some optimization work and all of that to be feasible there, but that's easier. The stochastic constraints is the tough one. And give me a sort of this 1 minus beta confidence level. I want to make a statistical statement on feasibility and infeasibility with that confidence, okay? So if you think about it, it's actually not that difficult. So if one thing I can do, I have this constraint, right? I'm going to basically form, like 1 minus alpha level confidence interval, upper confidence interval on that. And then check, if that upper confidence width is less than 0. And because it's a sample average, no matter what this thing is, right, I can use, actually, this is approximate 1 minus beta level confidence interval because we're using central limit theorem in the limit. But if n is sufficiently large, so this approximate confidence interval is going to work. This is the beta, 1 minus beta quantile of a standard normal. And I take just the regular sample variance of these individual estimators, and I check this quantity, right? If this quantity is less than or equal to 0, then I'm saying 95% confidence I have a feasible solution. Okay, so it's not that difficult actually, just you can use, because we have sample average, just a regular mean on the constraint only. When we optimize, it gets more difficult. So in this case, do this, check if it's less than or equal to 0, and you're done. Okay? So once you find such a solution, then you can go ahead and try to estimate it if it's, how good it is. Okay? One thing, what happens if this is not true? Right? If it's actually greater than 0. You have to have some method to find a feasible solution. And again, I'm sure Tito must have mentioned this. Right? So one trick that's typically used is to relax this constraint or make it tighter, right, when you have stochastic constraints. So if you make this, let's say, something less than 0, like negative epsilon for some positive epsilon, then, and you solve this sample average problem, your chances of finding a feasible solution to the original problem increases because you're actually constraining, tightening the region, right? So this is some kind of tricks you can use to find such solutions. Of course, you can do much more complicated things, exploit your structures here if you have some. But otherwise, you can check this statistically like that. All right, so once we're done with feasibility, as I said, we're also done with the estimating the objective function value, but now we need to find a lower bound. okay, if you want to estimate the optimality gap. We don't know what the optimal value is. So this has been suggested in the literature. Sometimes it works well for some class of problems, and sometimes it can be very loose. And you can see why. What are we doing? We're basically, if I go back here, this is my original problem, right? I have stochastic constraints and deterministic constraints. I want to get rid of that, put it in the objective. What do? I just use Lagrange multipliers. And so I get rid of the stochastic constraint. And for any positive lambda, I know from duality theory that I'm going to get a lower bound on the true optimal value, right? So, and under certain conditions, say for convex problems with some regularity conditions and stuff, and if we know the optimal Lagrange multiplier, then hey, we can actually, it's going to be a good bound, like a really good lower bound. Of course, two problems. One, I again have the same issue, right? This is just another expected value. My g now changed. My function is now g plus lambda times g1. So I'm back to the old setting, right? The one that we've discussed last lecture. So this is minimizing expected value of some function with some deterministic constraints. So if I want to evaluate a lower bound, what do? Solve the SAA, get it, and then just use that as a, so expected value of the sampling average approximation is less than or equal to that value, and so on and so forth, right? So that's what people have used, because you're back to the same problem. So you can use exactly the methods we discussed earlier, actually. All right? So you can use them regular. There are several methods we discussed last lecture, so you can use them. So one of them, for example, the multiple replications one. So you're going to do, let's say, m independent approximations. They're all this Lagrange thing. And then you're going to get these individual values. Now I parameterize the optimal value of the SAA with respect to lambda. I have m of them. Take the mean, take the sample variance. Again, even if I don't know what these are distributed as, I can always, if I do independent approximations, then I can use approximate or center limit theorem and form a confidence interval like this. But I'm going to form now a lower confidence, okay? Because I'm only looking at the lower end of things. So there's a minus and the quantile and the sample standard deviation divided by square root of m. That's the number of replications I have. All right? So one thing, so this is what we end up having. So I'm going to have, this is a Lagrange SAA problems, optimal value, right? On average, it's going to give me a lower bound on the actual Lagrange optimal value, which is definitely then less than or equal to the optimal value. And then this is any solution that's 1 minus beta % confident that is feasible. So I have these inequalities, right? And I can deal with this. I form a 1 minus alpha level confidence interval on the lower end of it. And then on this side, so this is a minus. And on this side, I form a 1 minus alpha upper confidence interval using the regular statistics. Once I do that, and as I said, you can use different sample sizes here. And obviously, you can use a much higher sample size here if you want, because this is easier, right? You're just estimating expectations. Versus here, you're solving M optimization problems, okay? They no longer have stochastic constraints, but they're still very difficult because those G's functions are not very easy to estimate. So, I mean, you can use this, you can use multiple replications by using the same observations, or you can use them separately, as I said, and you can do that for the other cases too. And if you do them independently from one another by Boole-Bonferroni inequality, you just take this, this part, this guy, and this one, and subtract from that. Minus that becomes plus, and that's my confidence interval on the optimality gap. But first, I have to check feasibility. After you're done, then you continue with these things. So one thing you need to be careful, obviously, is this is 2 alpha rather than alpha. So you might want to shrink your alphas on each one of them. Okay. Yeah.
Can we use the same strategy, even though we have two stochastic processes, one related to the constraint and another one related to the objective function?
Yeah, you can. What do you mean, same strategy?
I mean, is it the same interval? We get, I mean, not the number, but the same way to construct the interval, because we have to use different samples, right? One for the
Yeah, you can also use same samples, right? Do multiple replication. I mean, you can do multiple batch them and so on and so forth. You can do the same thing. You can do the one that I discussed last time, or you can do separately. Yeah. And it all depends on your your structure here, how hard it is to solve the lower bounding problem, right? And if you can shrink, so if you use a different sample size here, what's going to happen? You can actually shrink the sampling error quite a bit because this is a lot easier, all right? So you can increase that sample size, but here this is very difficult. So you can only use a much smaller sample size n, and then you're also limited to some number of m, right? One thing, if you do the same common random numbers that we discussed, there's actually variance reduction. So if you use the same samples here and do the batching type of thing that we discussed, then you reduce the overall variance. But again, it depends. If this is higher and you want to shrink it, then use separate version. If you want to shrink the overall variance, then use the common random numbers. Okay, so it's a little bit problem dependent how the variability of the problem changes. And but either one can be used. So from my experience, usually when you use the common random numbers, there's a lot of variance reduction. So it gives pretty good results. Okay, so, all right. Yeah, I have the comment here. So you can do that as well. All right, so one thing, this is all good, but one thing we haven't discussed. So first of all, I said we don't know the optimal dual, obviously, the Lagrange multiplier. But how do we even obtain this, right? Whatever we obtain is probably going to be statistical anyway, right? Because, we can stick in some number, but what, say, for example, Wang and Ahmed did, when they solve to obtain the feasible solution, they look at the, this is, by the way, must be independent from all the quality assessment stuff. Independent samples used here. You solve this problem, get your candidate solution, and then you look at the optimal dual multiplier of this problem, sample average approximation, and you can use that. Okay? And they've been reasonably good with this. When does it work? And I think that's pretty clear. You have to have some nice things happening. So when the true problem is convex and under these, say, Slater conditions, so on and so forth, regularity conditions, with the optimal multiplier, you have this equality. So you're kind of back to that the old setting, without stochastic constraints type of thing. Of course, you don't know this, but even if you don't, there's still more hope here, right? But if you have some kind of a duality gap, like integer programs or some other things, non-convex programs, then there might be a really bad duality gap here. So already without, even if you used actually star here, like the best thing you can do, it still has a gap from the optimal value in the best you can do. And then you find a lower bound on it, and on average, and then you find an expected lower bound on it. So it can be very, very loose, okay? So that's the danger. So you cannot use it for every type of problem. So for example, many chance constraints or probabilistic constraints, right? Unless they're, say, log concave or something, they're not going to be convex. So you're not going to have, this is not a very good method to use. Okay, so what do we do in that case? And that's my next topic, so to speak. All right, so you can use, it's a probability. Probability is nothing but an expectation, so it actually fits in that general expected value type of problem. But we can do something more. We can exploit it's a probability, and there's going to be binomials and Bernoullis, right? You're estimating probabilities, essentially. So you can use them and get some better results. All right, so again, for simplicity, I'm just going to assume the objective function is deterministic. And then there's only one probabilistic constraint. Of course, if you have joint probabilistic constraints, you can write them by taking the maximum of them to be, say, less than or equal to 0. You'll get the same thing. You can lose certain properties because the maximum operator will change some properties, but you can write even joint constraints with only one probabilistic constraint, right? So it's going to look like this. I'm minimizing, say, deterministic function right now, and then probability of some, now it's h, of xc less than or equal to 0. I want this to be satisfied, say, 90% of the time. All right? So our G1, the stochastic constraint, is basically 1 minus alpha minus the indicator function. If this event happens, it takes value 1. If it doesn't, it takes value 0. If I take basically this constraint is my constraint, which is the same as my chance constraint or probabilistic constraint. Okay? So the three problems, before we do, it's just a reminder, you have had a lecture on this in more detail, but the sample average approximation of this problem, right? Because I assume this is deterministic, you can also do sampling over there, but let's only focus on the constraint. So I just take a sample, same as usual, just use the indicator function. If this is less than or equal to 0, 1, otherwise 0. The one difference that we have made, right, we've changed the original parameter of the problem is 1 minus alpha. But again, we can change that. So if I make this to be larger, then I have a less conservative model, right? So in this case, I can have a better lower bound. So if you want to exploit this, you can exploit it a little bit, right? So if I need to meet the demands 95% of the time, now I say I need to meet the demands 80% of the time, my cost can go down, right? On the other hand, I can do the other way around, and then I will have a more conservative model. So now I want to meet the demand 99% of the time, right? So I'm more constrained. I have to do so much more to get to 99%. The cost will go up. So in this way, you can also ensure a feasible solution. If it's feasible to the 99% problem, chances are it will be feasible to the 95% problem, right? So you kind of reduce the sampling error a little bit by making a more conservative model. So you can play with the feasibility issue there. All right, so let's define P of x for a given solution x. This is the probability that this is greater than 0. Okay, and I'm trying to control that, right? Well, it's basically the violation probability. I want this to be greater than or equal to 90%, so I want that to be less than or equal to 10%. So it's the violation probability for any given x. And which means it's going to be feasible if this violation probability is less than or equal to alpha, according to my original problem. Now, do I know this? I don't know it. Can I estimate it? Of course. How do you estimate probabilities? You take samples, and basically you do the indicator function. It's the sample mean of the indicators, right? And that's our actually even more basic statistics for statistics probability classes, right? How to estimate probabilities. And then you know that this summation has a binomial distribution, right? It's basically telling me out of the n trials that I've made, they're all independently, by the way, we're doing IID, crude Monte Carlo. Out of the n trials, I'm looking at how many of them actually turned out to be this function is positive, all right? So it's a binomial distribution with the probability of success is actually my probability of violation, and a number of trials n, okay? So I can use exactly the same idea that we use for general expected value problem, just specialize it a little bit for probabilistic constraint. Remember, we took the sample mean, and then assuming n is sufficiently large, we used the standard normal quantile. But instead of using the regular variance, you just used binomial variance, and it's a little bit better than just using the sample variance. And then you can just say, hey, I'm 1 minus beta times 100 confident that it's feasible. So that's one way of doing it. There's another way of doing it, okay, which could be a little bit, give you better results. So if you remember, binomial, so we're going to see them. This is the probability of success, P, number of trials, N. This is the cumulative distribution function of a binomial with these two parameters, okay? It's written here. And this K, yeah, less than or equal to, number of successes being less than or equal to K. What was suggested is, okay, give me a parameter beta. This is my confidence level of how feasible the solution is, right? I define a quantity like this. So it's going to, for a given x, I look at this binomial cumulative distribution function. I fix my number of, this is my number of samples, right? I generated n samples. And this is how many of them basically violated my constraint. Right? This is n times p hat. This is my estimate of the violation probability. N times that will give me, say I did 100 samples, 6 of them violated. 100, 6. Now I look at this. What is the maximum, supremum of the probability of success that will give me this cumulative distribution function to be larger than beta? All right? What is that value going to be? So if you look at this, this is actually a random variable, right? So every time I do another sample, I do another 100 samples. This time, 5 of them violated. I do another 100 sample, 10 of them violated. So every time I do it, this thing is going to change. So this is actually a random variable, right, for a fixed x. Okay? You can show, the nice thing is, you can show that, and if you think about it a little bit, right, this violation probability for my solution x, that being less than this quantity that I've described, the probability of that happening must be greater than or equal to 1 minus beta. Okay, so it's the way we select this beta over here. And the original comes from, the distribution is actually coming from the probability of success of this, right? So when you see this, then it's immediate how you can form a feasibility. When is my solution x feasible? If the violation probability is less than alpha, right? That's my problem definition. So if I can find this value, I do sample. I estimate this value for that sample. And then if this quantity is less than or equal to alpha, I'm done. I'm basically, say, 95% confidence I have a feasible solution. Okay? So that's the way to do it. That's the feasibility assessment, second approach. Now, I want to, suppose we found the solution that's feasible. What's the next step we do? We estimate its objective function value. In this case, it's deterministic, I assume. But if it's stochastic, so it's deterministic, so we don't have to deal with that. We're mainly concerned with finding a lower bound on the optimal value. So again, just a reminder that we created our SAA problem and we parameterized our SAA problem according to, this sort of violation probability, gamma, right? So just I wanted to make it clear, so I wrote the optimal value of the SAA problem with respect to this parameter gamma. All right? I'm going to do multiple replications again. So I'm going to take m independent samples. Each one of them will have n observations in them, right? And once I do that, I solve my SAA problems, and I have a fixed gamma value. Again, I can play around with this, to get lower bounds. Or I can keep it the same way. So I'm going to obtain a bunch of these, and once I obtain them, instead of taking averages this time, we're going to do something different. All right? So before we were always taking averages and then calculating the variance and whatnot. So this one, we're going to order them. So these are the ordered statistics of these random variables, right, which are the optimal SAA values. So this is the smallest, say I did 10 of these. This is the smallest value I got, second smallest, and this is the largest value I got. All right? So why am I doing this? Because Shapiro and Nemirovsky, this is from them, you can show for any order statistic, right, take the Lth one, obviously it has to be less than or equal to m, greater than or equal to 1, right, however many I do. For any one of them, you can show that the probability that, let's take the first one, right? The smallest order statistic will give me a lower bound on the true optimal value. The probability this will happen is going to be greater than or equal to another binomial probability, all right? So that binomial probability is what? I have done m trials, right? So that's fixed. And then this L is my order statistic. So if it's the first one, you can think of it this way. If it's the first one, this probability should be higher than if it's the last one, right? So the first one giving me a lower bound must have a higher probability than the highest one giving me a lower bound, right? And if you look at this L minus 1, or 1 minus L minus, so L minus 1, if it's 1, it's going to be what, 0. So binomial less than or equal to 0, there's only one value. So out of the m trials, you get no violations. All right, if you use the first one. If you use the last one, 1 minus, you get m minus 1 violations, which is, you only look at the probability of the m, right? So it's actually less. All right, so if you use the first one, you can get, obviously, a higher value here. And then this one is a little tricky. This one depends on, well, the inner problems, right? So how many samples you did to get these estimates. Each SAA problem, the sample size. And then this alpha is the correct violation probability for my problem. But where I cut off the cumulative distribution function is depending on gamma, all right? And if you do this and you plug it back in there, you can show that this probability will be violated by that. All right, once you have that result, then I think the rest is clear. What am I trying to do? I'm trying to come up with, say, 95% confidence, some value, say confidence interval. That's what we did before. We take the means, we added some sampling error using regular statistical theory. We said, oh, I'm 95% confidence, approximately or in the limit. It's going to be less than or equal to, my optimal value is less than or equal to my confidence thing, right? Now, I have this one. So if I want to have 95% confidence, what do I need to guarantee here? At least 95. Something 5%, right? If it's less than or equal to the 5%, I will get essentially at least 95 or higher, okay? So basically it comes down to picking these parameters, all right? So how many to sample for each inner problem. So there's some computational cost here because solving those problems are difficult. This is the number of replications. Right, this gamma is, if you want to get a lower bound, you can play around with it, better lower bound. But then also you lose because you don't want the lower bound to be too loose, right? So there's a bit of trade-offs, computational trade-offs and the probability trade-offs and so on and so forth. But if you can find parameters like this that satisfy that, then you're basically done, right? So you have found a value that tells you, hey, with at least 95% confidence, your optimality, your optimal value is going to be larger than that. Okay, you found a lower bound on it. So instead of using that, confidence interval, you can directly use this value for this chance constraint. Okay, and you can embed it with the upper bound, and that again you can get 1 minus. Not 2 alpha in this case, alpha beta type of thing. All right, so this is one possible value. So use the smallest one. As I said, it will increase the probability as a lower bound. Take this to be the nominal sort of violation probability. If this is really small, you need a larger sample size. This also makes sense, at least 10, so that you have some statistical estimation, right? Beta small, so that you're sure, and then M also you need to have at least 10 to have some kind of statistical meaning, even it might be small. But there's some, actually, some work that Bernardo and Shapiro and all of that did, and they have a lot more in here, so in some computational considerations. I'm not going to get into that. But just to give you sort of a gist of how to do this assessment of solution quality, feasibility, upper bounds, lower bounds, on different types of problem. And that's what I have. And that's the only word I know. Obrigada. All right. Well, thank you. Any questions? All right, so I'll leave it to Tito. It's actually a nice topic. He's going to talk about probability metrics and how to use them for scenario generation and reduction.